So let's go on. So that's basically what we did before. Let's now move forward. So let's look at some of these. We're going to go on now to the other side of the page, which is now for expansions. So we've looked at compressing the flow. Now we're going to say what happens if, instead of putting an obstacle, if you like, in the way and creating a shock, what happens if we now actually drop the surface and give the flow molecules more room? Now they can expand. What are they going to do? Well, they're going to race faster, so the Mach number goes up. It's not going to be so crowded, so the density goes down on the other side. The pressure goes down, the temperature goes down. So it's the opposite effect, shall we say, to what the compression, the shock is. And what happens is you get what's called an expansion fan. Each of those is actually what we would call a Mach line along there. So in other words, what's happening is bit by bit, the flow is changing its Mach number from this one here into, if you like, region 1 in this case, into the Mach number at region 2, bit by bit, and it's fanning its way, so it's actually gradually expanding as it goes. Right, now, how do we actually calculate what these values are? That's where you need this particular table. Now, on the back of this table, it says it's a Prandtl-Meyer function table. And it writes the Mach number down, and it writes an angle which it's got as a Greek letter nu. So what on earth is that? Nu is defined as the amount, if you like, what angle would I need to make the flow go around the corner if it started from Mach 1 and I needed to get to, say, Mach 2. So you can see on this table, if I've got Mach 1 and Mach 1, I don't need to allow it to expand in any way here. You can see it says that nu would equal 0. Whereas if I look at Mach 2, I'd need to make sure it was an angle of 38 degrees. And that would give me exactly Mach 2 on the surface here as the flow went down in that direction. If I'm going from not Mach 1, say this was Mach 2, and I want to go round the corner there to say Mach 3, you'd find out what the new value here was for Mach 2, and you'd find it out for Mach 3, and you'd take one away from the other, and that would give you the conversion from Mach 2 to Mach 3. Okay, so that's actually how to read these, so it's actually quite simple in what's going on. So, if you look in the books, it doesn't always come out like that. What they often show you are things here. You can see a nu angle, and mu is the one that is the sine to minus 1 of 1 over the Mach number. So they also come in tabular form as well as sort of, hang on, a slightly different listing to this one, shall we say, in most textbooks. So, note that when the flow went across the shock, it's always parallel to the surface. And when the flow goes round an expansion, the flow closest to the surface still follows it. So we're not dealing with any cases here of separation. The theory here is assuming that everything is always properly attached. There's also no viscosity in this. This is purely the pressure. So if you wanted the total effect, you'd have to add in the boundary layer drag using the formula you were using before with Abdeslam. So this is solely the pressure changes. Right, so we've got here the flow moving from region 2 to 3. So we've got Mach 8 degrees on this, top and bottom, symmetry, 0 degrees, Mach 2, it's coming up here and then going down and so on. So it moves from region 1, there'll be a shock wave there, region 2, expansion to 3, or from region 4 to 5, and basically, what's the change in angle between region 2 and 3 that the flow experiences? It's purely geometric, so whereas in the shock case, everything's to do with, you've got to be careful in that sense of what the value is before and so on. In the expansion value in terms of degrees that we're interested in solely comes from your geometry. So in this particular geometry, the flow's coming along the surface of region 2, and it needs to turn to go down the surface of region 3. What's the angle that it turns through? So, 16. Why? Because if we didn't have any change, it would go up here. It needs 8 degrees to go back to the horizontal, just like here. And needs another 8 degrees to come down because of this. So in other words, it's the sum of this angle at the front and this half angle at the end. Leading edge and trailing edge half angles. Okay, well done. So let's see what else we got on there. We've got expansion waves. So we've got 16 degrees there. Expansion's a function of geometry, not of the angle of attack. It doesn't matter if I didn't put this at 0 degrees and I put this at 5 degrees. The expansion angle is still 8 plus 8 is 16 because it's just the actual geometric effect. Okay. The right one on that one, there it is. Right. So, question, free stream map numbers 2. Region 2, the map number, you can work it out for yourself, but I've given it to you in a moment, it's 1.72. What's the Prandtl-Meyer angle for map 1.72? 1.72. Okay. Are you okay on this? All hovering around 1.72. Look to the new value, and let's hope 18.4. You all okay on that one? So on the table, 1.72 Mach number gives us 18.4. Excellent. Right, well done. So if it's 18.4 corresponds to the Mach 2, and we now want to go round 16 degrees, we have to add 16 on. So what do we get? 18.4 and 16, 34.4. Okay. So if you use this and you find 34.4 degrees, what's the Mach number? 34.4. Okay, roughly. So what you should find is about 2.3, 2.31. In an exam, we will accept from this the closest. You do not have to worry about interpolating or interpolating between two values. Take the one that's the closest. If it's halfway and you think it's absolutely halfway, then you can have 0.305. But if it's halfway, then take either. It'll work. We will make sure in our spreadsheets that we actually will work it to the value. So take the closest one, don't worry about interpolation. Right, so if you've got the idea of that, find the Prandtl-Meyer value of mu before it starts to expand. Add on how much the geometry says it's going to expand. Find that total angle, and that will tell you what the Mach number is of the flow once it's gone round that particular corner and is going back on its way. Right.